In this slide, we are going to digress and we are going to talk about lines and plane determined by points and normal. We'll focus on the word normal. When we say that a vector is normal, it also means that it is orthogonal to something. We begin with this example in R2, and where we have a line y equals to mx plus c. When x is equals to 0, y is equals to c, and this is the value here, c. When y is equals to 0, mx equals to minus c, therefore x equals to minus c over m, which is the point here. In this case, the slope is sloping towards the left, and therefore m is a negative value for this example. So this is the typical way we express y. There is another way we can express this equation. It is called a point and a normal. What we do is that we find a point on the line, and we also find the normal vector n to the line. The idea is interesting. Once we have a point on the line P0, and let us now find another point P. Well, in this case, P can be any point x and y on the line. So therefore, now from P0 to P, it is a vector along the line. Once we have this vector, since n is normal to the line, then the dot product of P0 to P and n will be equals to 0, which is defining that n is normal or n is orthogonal to P0, P. It may seem to be a chore to learn a new way to express a line. However, now if you think of a 3D world, this representation is actually very efficient. Let's repeat the point normal expression for a R3 issue or problem. We have a plane in R3, the gray area. Let us find the point normal equation or expression for this plane. Let's first find a point. Let's call the point P0 with coordinate x0, y0, z0, and it is sitting on the plane. Let us use another point, and this point we assume that it is on the plane and it can be any values x, y, and z. Therefore, from P0 to P, it is a vector on the plane. Let us have another vector, n, which is a vector that is normal to the plane. And this vector has coordinate a, b, and c. To find the expression for the plane, we begin with P0 to P, dotting with n will be equals to 0. If we express P0 to P as a column vector, what we have is actually x minus x0, y minus y0, z minus z0 for this vector. We are dotting with n, and in our example, n is a variable, or n is a vector with coordinate a, b, and c. A vector dotting with another vector will give you a scalar. When n is the normal to P0 to P, the scalar is 0. We open up the expression and we have A, x minus x0 plus B, y minus y0 plus C, z minus z0, and the whole expression is equals to 0. When you continue solving for this, you have ax minus ax0 plus by minus by0 plus cz minus cz0 equals to 0. We then we move the variables to one side. We have ax plus by plus cz is equals to ax0 plus by0 plus cz0. We call all this maybe just a variable because they are numbers, we just have d. What you should take note now is that the coefficients of the normal vector n is clearly seen in A, B, and C as coefficients of the equation here. If you wish to have a good explanation of why are the coefficients of a line or plane are the normal vector values, have a look at Khan Academy. Google Khan Academy normal vectors from a plane equation and you will land in this page. In this page, he did a 10 minutes explanation of a R3, showing very similar examples as we have just done. Lastly, we work on example 2, the second part of example 2, where we have the plane equation given by this expression. And the question asks us to find the normal to the plane. All we need to do is to expand this 4x minus 12 because we are multiplying 4 by 3 plus 2y minus 5z, and minus 5 times minus 7 is plus 35 equals to 0. All we need to do is to move the expression having all the variables x and y on the left hand side, and we have plus 12 on the right hand side, minus 35. Simplify, we have minus 23 on the right hand side. And now we can identify the normal from the expression on the left hand side. The coefficients 4, 2, minus 5 are the normal, are the coordinates of the normal for this plane. Please remember that the normal is through the point P0. How do we find the point? In fact, it is already shown in the equation over here. X minus 3, y with no numbers, z minus 7. The values of x and y and z that give the expression in the round bracket to be 0 are the coordinates of the point, because only then is the left hand side equation equals to the right hand side, which is equals to 0. This concludes our short discussion on using points and normal to express lines and planes.